Hello everyone, my name is WencongXie, and today I'm very excited to present my project titled Handwriting Transcribing Text using the deep learning technique. In this project, I have designed and implemented a deep learning model to recognize handwriting characters using the MNIST balanced dataset. So let's start with a quick introduction. So what is the handwriting text recognition? Handwriting text recognition is a process of converting handwriting characters into machine-readable text. Unlike printed text, which was standardized fonts, handwriting text varies significantly depending on the writer's style, making it a unique and a complex task. So why is handwriting recognition challenging? It depends on the variability. Each individual writes differently with unique lengths, spacing, and shapes. Everyone writes very differently. And such as certain characters, such as 0 versus big O, like B versus 8, they are pretty similar to each other. And there are also some complex symbols. Well, handwriting lowercase like G, Z, or Q can be like very difficult and inconsistent. And also, there are also some noise, some smudges, faded ink, or scanning errors. Such things can cause some big noise to handwriting recognition, which is very complicated. So my objective is to develop a deep learning model that can effectively recognize handwriting characters from the MNIST balanced dataset using a combination of convolutional neural networks, which is also the CNN for feature extraction, and bidirectional LSTM layers for sequence learning. So to achieve this goal, I use the MNIST balanced dataset, which is publicly open source. And here are some key details about this dataset. So first, it contains 47 classes, including digits from 0 to 9, the uppercase letters from big A to big Z, and lowercase letters from small a to small z. The dataset also includes 112,000 training samples and nearly 18,000 of test samples right here. And each engines in my own project is 28 times 28 pixels and grayscale. On the bottom side of this PowerPoint, you can see a few sample images. The first images is the raw data set, which is only showing the label number. You can see the first one. The first one is the 31. Second one is the 35, and third one is the 30. This is the label number. And after the some data processing by myself, I just turn it into a right one. You mean the right one? This V, this is Z, and this is U. Something like that. I can make this an excellent data set for me to train and test my model. Yeah. So here's a quick review of the architecture I designed. So first, the CNN layers, which is also the convolutional layers. The model starts with two CNN layers to extract spatial features like edges, shapes, and textures. And for batch normalization and the max pooling here, you can see right here in the diagram here, they are applied to stabilize learning and reduce the dimensions. And for the flatten layers here, it prepares the data for the LSTM. And on the LSTM layer with 128 units, it just processes the sequential patterns from the flattened features. And I also add two dense layers. The first one here is 128 neurons, and on the ReLU activation followed by dropout for regulations. And on the final dense layer outputs here just probabilities here for 48 classes using a softmax activation, which also they're all showing in the diagram right here. So this design just effectively balances the spatial feature extraction and sequence learning, making it perfect for me to do the handwriting text recognition. And so here we go to the pre-processing and data preparation. In terms of the implementations, here are a few key aspects. So the first one is the pre-processing. I normalize the pixel values to 0 and 1 and apply the one-hot encoding for the labels. For the dataset preparation, I use TensorFlow's map. Because you can see here's a screenshot of my code. I use the TensorFlow's map, batch, and prefetch functions to optimize data loading. And for the callbacks, I implemented 3 callbacks to improve training. I do this because I feel so many times in the training stage, because sometimes the data just stop training, like they stop training at stage 6, stage 7. That's not what I am looking for. I set the training epoch to 20, to at most 20, and I expect it could meet maybe 17, 18, 19, something like that. So in order to do this, I apply this technique right here. So for the early stopping, it can prevent some overfitting right here. For reduce LR plateau, it can adjust the learning rates dynamically, and for model checkpoint, it can make me easier to save the best performing model, which is perfect for me. Yeah, so here we go to the training process. To train this model, I use the following settings right here. The first one, I set the epochs to 20. The optimizer is Adam. It's well suited for complex deep learning models, which is also I learned from the class. For the loss function, it is the categorical cross-entry, since we are dealing with a multi-class classification problem. And for the metrics, for the accuracy one, it is to evaluate the model's performance during training. I trained the model for a maximum of 20 epochs and a batch size of 64, which is I expected to do. And the training was performed on the M&S balanced datasets. I also used the prefetching to speed up data loading and improve some training efficiency. So here is what I observed during the training stage. The training accuracy here is steadily increased. You can check from the small images from here, because yeah, I just show it here. Well, the validation accuracy around 88%. There's a trend of overfitting. But it was addressed by the early stopping, which I mentioned before. And it's also stopped the process at epoch 70. So let's go back to the code. Well, so you can see the code here. So for the epoch 17, early stopping, restoring model weights from the end of the best epoch 12. So let's go back to 12 here. You can see here. There we go. The val accuracy 0.8813, val loss 0.3967. So that is the perfect one, which I expected to do, and this also works. Okay, so yeah, overall, I think this training pipeline just can ensure that the model achieves strong performance while preventing the unnecessary overfitting. So let's look at the final performance of Fido on the tested set. So you can see this is a picture which I showed before. The test accuracy 88.13%, test loss 38.48%. And these results show that the model generalized well on ANSI handwriting characters, and the model successfully learned to recognize 47 classes of handwriting digits and letters. Despite some challenges like visually similar characters like 0 and big O, the accuracy here is very strong. So here you can see the screenshot of my evaluation result here. Yeah. So here's the result too. I also created 2 graphs here. On the left graph, you can see that the training versus the validation accuracy graph. So from the graph, training accuracy reaches up to 97.5%, while the validation accuracy just displayed at 88%, which I generated from the graph. This indicates that the model has learned well, but starts to overfit slightly after epoch 10. So on the right graph, the training versus validation loss graph shows a very steady decrease in training loss, while validation loss stabilized around 0.4. So I think the early stopping just stop training at epoch 7 to prevent further overfeeding. That works in this graph. This can embody the graph. Yeah, it's very perfect. And here we go to the challenge encountered. I did facing a few challenges. So the first one is the overfitting. After epoch 10, like some experiment before I implement such perfect code, the validation accuracy plagued with while training accuracy continued improving. I addressed this by using the early stopping and dropout. The second one is the ambiguous characters. Characters like O, big and 0, or big B and 8, which I mentioned before, they often just cause some misclassifications because of their visual similarity. It's very complicated. And the third one, some complicated symbols, which I will mention after this slide because it is showing the demo. It will be perfect for you to check it. Yeah. And all the things here is to reduce the unlearning rate dynamically and improve stability. Well, for the future improvements, to further enhance the performance of these models, I did some future consideration. The first one is the data augmentation. I can just apply some random rotations, shifts, and noise, which can help to improve the generalization. And second is the transformer-based models. I can use some transformer, which can just possibly improve the accuracy by better capturing the long-term dependencies, which I already did. And last one is the hyperparameter tolling, which is a little bit complicated. So this one is the optimizing the LSTM units, dropout rates, and learning schedules. Like this could further boost the performance. So let's do some simple demo of the code. All right. So in this demo, I will just display some predictions for a few random samples from the dataset, and you will see that the true labels and the model's prediction above each image. And I'll just cut it short. Yeah. So let's jump out to the last part. Yeah. So I write this function, which is also showing in the short video, the 3-minute video. This is the function of showing my result to the audience to let them see it clearly. And I set the n to the 45 here, which is the maximum, the batch number size. And after training that, there we go. We can just pick some random number from 0 to 45. Okay, so let's just start with 5. Well, we can see that it perfectly just matches the result here. The prediction is A and true value A here. Prediction is B, true value B here. Let's see 20. Well, you can see most of them are perfectly just matches with each other, but you can see here, okay, prediction E, true value is F. So when you look at this image, you can just decide clearly whether of these images is E or F. And you can see this image, prediction G, true F, it is exactly the same work. So that's the problem, and I need to just address it. And here is the all code from like load dataset, data pre-processing. I view the sample images here, which is also I mentioned in my presentation before, and also just view the all data sets here, training stage. Like I generate the training validation accuracy graph here. Yeah. And so I successfully just implemented SEN and LSTM model to transcribe such characters, and the model achieved a text accuracy of 88%, which is very good and very strong. And I think this project just highlights the challenges of handwriting representation and propose future improvements to further refine the accuracy. Yeah, here's the reference, and thank you for listening to my presentation. Thank you.